Okay, now we're going to look at rate laws. Okay, so just a simple definition. A rate law is a mathematical relationship that relates the rate of a reaction to the concentration of the reacting species. And so an example of this, you see a lot of these in the textbook. An example would look something like this. Rate equals K times the concentration of A, where A is the concentration of one of the reactants. And this K is called the rate constant. And this one that we've drawn here, this is just one particular rate law, but the form of that algebraic equation can differ, in fact does differ, for different reactions. Okay, let's take a look at some of these. Okay, so in general, we can describe a general form for a reaction. And so if we have a reaction that looks like this, so this is our reaction, and capital A and B are our reactant species, the two things that are reacting. Capital C and D are the product species, and the lowercase letters here, A, B, C, and D, are the stoichiometric coefficients. Okay. Now what's important about this is that for a chemical reaction, we're talking about kinetics. The rate is always going to be some rate constant times the concentration of the reacting species, each raised to some power. So I'm going to put an X here and a Y here. Okay. And what's important about this is that if you notice, this X here, this exponent on this is not the same as the stoichiometric coefficient in the equation. And this Y here, the exponent on B, is not the same as that stoichiometric coefficient. Now, sometimes it turns out, just by coincidence, that they are the same. Okay, so sometimes they can be the same, but they aren't necessarily the same. The point being that if you have a balanced equation, you can't just look at the equation and determine the rate law from that equation. In order to determine the rate law, you've got to do some experiments to figure out what those coefficients X and Y are. And also, those coefficients X and Y determine what is called the order of the reaction. Or you could also say those coefficients X and Y determine the reaction order. Some people say reaction order, some say order of reaction. But the order of reactions is determined by those two coefficients. Okay. All right. So let's look at a couple of examples, and I'll show you what I mean by the order. Okay, so here's a a chemical reaction. 2 molecules of N2O5 decompose to give N2O4 and oxygen. And the rate law for this reaction is rate constant times the concentration of N2O5. Okay, and so what this means is, if we just write the rate law this way, K times N2O5, that means there's an understood 1 there. Because if you don't write an exponent, that means that the exponent is a 1. Okay, I'm going to go ahead and erase that because we don't usually include the 1 there explicitly, but it is there. Tell you what I'll do. Put it in parentheses this time. Okay. All right. So this is our rate law here. And again, notice that the coefficient here is not the same as that exponent. In order to determine what the exponent is, you have to do some experimentation. And there's a section in the book that talks about how to do those experiments. We're not going to worry about that just yet. That's a topic for another section of the book. You can read that part if you'd like. But I just want to talk about this rate law. And if we have a rate law where the exponent on the N2O5 is a 1, we say that this reaction is first order with respect to N2O5. And we also say that this reaction is first order overall. Right? The overall reaction order is the sum of the reaction orders for all of the species involved. And since this one only has 1 species, the overall reaction order is the same as the reaction order with respect to N2O5. Okay. All right, let's take a look at another one. Okay, so here's the second reaction. 2 moles of NO2 react with 1 mole of fluorine to make 2 moles of NO2F. And in this case, the rate law is rate is equal to K, and that's our rate constant. And I should clarify, the rate constant is different for every reaction. So the K that I just had in that last example is not going to be the same K as it is for this example. The K has to be determined independently for each reaction. Okay. All right, so our rate law in this case is rate equals K times the concentration of NO2 times the concentration of fluorine. And again, since we haven't written any exponents up here, right? That means that those are presumed to be 1s. Okay, so when we talk about the order of this reaction, we would say in this case reaction is first order with respect to NO2 and first order with respect to fluorine, and here's where it's different. Second order overall. Okay, and again, the overall reaction order is just the sum of the reaction orders for each of the individual species. Okay. All right, so go ahead and take a look at this one. Determine what the reaction order is with respect to, oops, I just gave everything I wrote it down wrong. Okay, hold on a sec. There's a 2 there. All right. Determine the reaction order with respect to NO and the overall reaction order. All right. Since there is a 2 up here, since that exponent is a 2, that means that it is second order with respect to NO. And since NO is the only species here, the sum of all of the reaction orders is also 2. So the reaction is second order overall. All right. I want to show you one more of these because it's a little bit weird. Okay, this reaction is the biological metabolism of alcohol. So this is a description of what happens in your body if you drink beer or wine or liquor, right? The ethanol that you ingest combines with oxygen in your cells, creating CO2, which you exhale in your respiration, and water. And this whole process is governed by the existence of enzymes. So this is a enzymatic reaction. A lot of biological reactions work like this. And for this particular reaction, the rate law is rate equals K. Now what's weird about this, I told you this one was going to be a little bit weird. What's weird about this is the reactant species, the ethanol and the oxygen, don't appear in the rate law, right? The rate is just a constant value, K, this rate law, regardless of what the concentrations of ethanol and oxygen are. So, and we do get rate laws that look like this sometimes. And as I said, particularly when you have something that is controlled by enzymes, biological reactions, and some other catalytic reactions. Now this rate law, we could rewrite this way. Could write this as rate equals K times the concentration of ethanol to the 0 power, right? Because anything raised to the 0 power is equal to 1, right? And rate equals K is the same as rate equals K times 1. Okay. So when you have one of these rate laws that just looks like this, and there are no chemical species in the rate law, then you can think of that as including the chemical species, except that the exponent on the chemical species is a 0. And so for that reason, when we have a chemical reaction that gives us a rate law like this, we say that it's 0th order with respect to the ethanol, and we can also say that it's 0th order with respect to oxygen, and following the same pattern we had before, the overall reaction order would also be 0th order. So this is an example of a zeroth order reaction. So here's how a rate law problem might work. One, of course, as we said before, you should be able to look at a rate law and tell whether it's first order or second order or zero order. So you should understand that terminology. But as far as calculations go, you might get a problem that looks like this. It gives you a reaction. Sulfur dioxide reacts with bromine to make SO2Br, and you've got a balanced equation there and a rate law here. Okay. And some data is given to you that when the concentration of SO2 is 0.15 molar and the concentration of bromine is 0.026 molar, the rate is 5.2 times 10 to the minus 6 molarity per second. And then a typical question here might be, what is the value of the rate constant? Okay. So to solve this, we can really just do some simple algebra. And notice for this, we've got 4 different variables. And this question could really be asked in any form with 3 of those variables given, and then you're asked to calculate the 4th, the one that you don't know. Very often you're calculating the rate or the rate constant, but it could really be any of them. And the key is just to do a little bit of algebra here. And since we're trying to solve, in this case, for the rate constant, right, we can get the rate constant K by itself if we just divide both sides by the rate, right? So algebraically, if we redo that, we get K equals rate divided by concentration of SO2 divided by the concentration of bromine. And then we just plug in the values that we've got here. And when we do these for rate problems, it's really important to look carefully at the units. And the units are going to cancel differently depending on the reaction order. Because if you've got one that's second order, like this one, then you've got molarity down here at the bottom twice. If you had one that was first order, you'd only have molarity down there once. Right? And if you had one that was zero order, you wouldn't have molarity down there at all. Right? So the units are going to vary depending on the reaction order. So let's take this and see what we can cancel out. We've got a molarity in the numerator. And we've got 1 molarity that we can cancel out in the denominator. Okay. This molarity here is going to remain since we don't have anything to cancel it out. So we're going to have 1 molarity in the denominator of this calculation. And we put that in calculator. I got 0.001333 per molarity second. I apologize for the small handwriting. I'm going to go ahead and erase this so I can write that a little bit larger. All right, so I got 0 0.00133 per molarity second. And if you go back and look at the values that were given in the problem, you see that all the things we were multiplying and dividing together had two significant figures. So that means we should round our result to two significant figures. And so K is 0.0013 per molarity second. Of course, you could also write that as 1.3 times 10 to the minus 3 per molarity second. And there's our answer. So for other problems and rate laws, you have pretty much the same process. It's just that instead of solving for the rate constant, perhaps you'd be solving for the rate instead, but or solving for the concentration of one of the species. But in all cases, all you need to do is take this rate law and just rearrange it algebraically to solve for the thing that you don't know, and plug in your values and go ahead and calculate. And of course, be careful about the units. The units on rate constants are very important, and also be mindful of significant figures in your result. All right, that about does it for rate laws, and we'll have a few other videos on first and second order reactions and things like that. All right, I look forward to seeing you later with another video.